personal friend of mine, Dustin Getz, who actually used to write Scala.
Yes.
Before he defected to the dark side. And now he does Clojure script. There's a bit of a friendly rivalry between Scala and Clojure. They're the only two functional programming languages that run on the JVM, after all. Just yesterday, Dustin was telling me how Clojure adoption is shrinking 10% a year or whatever it is, and I'm like, oh yeah? Scala is shrinking 40% a year. Sorry, that joke was for the Scala developers in the audience.
All three of them.
All three of you. So anyway, I'm very excited to hear what Dustin has cooked up. He's going to be talking about a really incredible project he's working on called Electric Clojure, which is a way of solving a problem that has, I think, plagued us since the dawn of client-server programming. Yes, it's a way of solving many problems, but one of the main problems it solved has plagued us since the dawn of client-server programming. So you're going to see some out-of-the-box thinking, some very exciting stuff here, cutting edge, pushing the frontier. I'm very excited to see what he has cooked up for us tonight. Please help me welcome Dustin Getz to the stage.
Okay, differential data flow for user interfaces. This is a talk about the computational structure of user interfaces. Who has used React? So React is one computational structure for user interfaces. Electric Clojure is a different one. And the best way, in my opinion, to teach a computational structure is just to teach a notation for it. So I'm going to teach you electric, and then you're going to learn the computational structure it encodes. And at the end of the talk, you can decide for yourself if differential data flow matches the structure of a user interface. Okay, so here we go. So what are we looking at? Electric is an experimental programming languages approach to user interfaces. We try to solve the front-end, back-end connection, the network connection, with a compiler. So as an example app, this is the 2 clocks demo, and there's a server clock and there's a client clock, and we're subtracting them. And this application is defined as a single function. The whole program is 12 lines of code. And you can see we mark the server parts, we mark the client parts. So this is actually a full stack application, all defined in these 12 lines. It's a client-server system with a WebSocket, okay? So you can see there's a clock on the server, a clock on the client. S and C are the stream of values from the clock, okay? It's an event stream. But you can also think of it as the latest value of the clock, here, if we're reasoning equationally. So here is Clojure script's subtraction operator, and we are auto-mapping it across the asynchronous types. Okay, so the compiler is injecting the effectful boilerplate for the underlying concurrent, the async type. Okay, and because the whole program is reactive, front end and back end, every point in the program is reactive, which means it feels like nothing is reactive. The types cancel out. Okay, so you will never make an error with respect to a mismatch between a synchronous and an async type. You can forget about them. Okay, DOM rendering happens on the client. It's not on the server. There's no server-side rendering. There is no virtual DOM. There's no React.js on the page. Because Electric is fully reactive at the programming language layer, there is no need for that. The Electric DOM layer is about 500 lines of code. It's very simple. Okay, so how does all this work? A good intuition to remember is UIs are streaming DAGs. So what this eDefin macro does is it analyzes this Clojure script syntax and compiles it to a DAG with a custom analyzer, okay? So let's take a look at the DAG. So on the server, we have the server clock bound to S, and then we have the client clock bound to C, and S is used in 2 places. So let's draw the DAG here. And then C is also used in 2 places. So let's draw the DAG here. And then the result of the subtraction function is used by this one DOM text node, okay? So there's the DAG. So what happens next is the compiler needs to figure out the network connections. So what it will do is it will look at your client server markers, and it will basically draw a box. I'm going to use a different color. a box around the server, okay? And it draws that same box right here. So now it's actually really obvious where the network crossings are. This is a network crossing because the S is on the server and it's needed on the client, okay? So the compiler will inject a WebSocket hop here. Okay, and since the computation is already asynchronous, there's not impedance by adding an async network traffic here. You're just adding a delay on something that was already a stream of events. Okay. So as I need that back. As the clock fires on the server, the S fires, and it'll send a message over the WebSocket, and then the client will receive it and just continue propagating through the DAG because the DAG is shared. Okay, so the DAG drives two things, reactivity, but also the network crossings. Once you start to see UIs as DAGs, it lets you think about this client-server system as not two separate things, but one holistic thing, a holistic system. So that's the trick. Okay, what else does the DAG get you? It also gets you concurrency. S and C, S is on the server and C is on the client, so this is two different variables on two different places in a distributed system. You could not make them run in statement order if you wanted to. And that's clear from inspecting the DAG. S and C have no edges connecting them, so there's no causal dependencies, okay? So electric let statements are concurrent. In fact, all of electric maximizes concurrency based on the DAG. And this is a departure from Clojure semantics where let statements run in statement order. But it doesn't matter to the extent that your code is referentially transparent. And a lot of Clojure code is, including macros, tend to be referentially transparent. So we're backwards compatible with most pre-existing Clojure libraries. Okay, so if you're like me, right now you're thinking, this is very cute, but what are the problems at scale when you try to use this? Lost my hotkey. Here we go. So we've all been burned by failed abstractions, object relational impedance mismatch, object-oriented programming, GraphQL, distributed objects in the 90s. Okay, so the question is, what are the problems we're going to encounter writing user interfaces, and how can this structure solve them? And many of them are very obvious. We have reactive rendering, we have the server connection, we have request waterfalls. Others are really subtle, and they only show up when you start to scale, such as query cancellation, control flow, dependency injection. And then you have the good stuff, virtual scroll, incremental collections, back pressure, streaming updates, optimistic updates, okay? So what we're going to do through this talk is we're going to go through a series of examples and map those examples to these problems and understand the computational structure you need to solve them, okay? So I'm Dustin Getz. I work on electric. And then around the halfway point, we'll motivate differential data flow and how that's the missing piece to scale UIs all the way. Okay, this next one starts to get more interesting. What we are going to do is traverse the file system recursively on the server, and while we're recursively traversing, we're going to cross the network and we're going to render it to the client in the DOM structure, this recursive DOM structure, and we're going to do this in a single recursive traversal, not two traversals. Okay, so first let's demonstrate the application, right? It's reactive, it updates as you change. This input is here. Here's your DOM input. This is a signal of values that are coming out of that input. Handle is the file reference. Here's the Java IO file. It's over a directory on the server. And remember, this is a Java reference. It doesn't serialize. It can't cross. So handle is on the server. Search is on the client. Server client. So starting on the server, is the file a directory? Yes, it is. Cond is Clojure's if statement. The cond is on the server. So now we enter this block, switch to the client, render the LI, render the text node in the DOM. What's the value that goes in the text node? Switch back to the server. It's the file handle. Get the name, switch back to the client, render the UL, switch back to the server. List the children of the files at this point. Loop over the children. Recursively, in the middle of the loop, go back to the top, right? Server, client, and so on. Now, you're probably wondering, when I keep saying switch, you're scared of request waterfalls at this point. Okay, but recall that UIs are streaming DAGs, so that's not how this works. Let's take a closer look at the DAG. The file handle is on the server, the cond is on the server, which means the outcome of its directory method call and the outcome of the cond is known on the server. Therefore, the server knows immediately that we are entering this block and we are not entering this block, okay? And now this client is merely lexical. Remember, the server and the client, they share the source code, and they know what each other wants. We can look into this frame and see, oh, the client is going to need the result of the get name effect, okay? And it can stream that to the client without the client asking for it, okay? If you look, if you know the outcome of the cond, there's no other control flow between the cond and this get name call. There is no dependencies on the client that are needed to do this, okay? And it's the same with the loop. Once you know the outcome of the cond, you can synchronously list the files, you can do the loop, and then you can do the recursion, and this is all eager and synchronous without a single dependency on the client, okay? It is just streaming the outcomes over the wire, and then the client catches the ball like a sports team and just picks it up and continues propagating the DAG. So the point is, shockingly, there are no request waterfalls. Everything is choreographed statically. It's all been planned out in advance. UIs are streaming DAGs. Okay. The DAG also gets us object lifecycle. So this is a very simple demo. It is a blinker. Here is the DOM H1 and the text node with the blink. Okay. Here is the if statement. Is even is switching between true and false based on the clock. And when it is true, you want to mount the blinker function, render the DOM H1, and then render the text node. And what happens when the is even signal turns false? Well, you want to unmount the blinker function, dispose of the DOM text node, and dispose of the DOM H1. Okay? So when you dispose, you're basically propagating the DAG backwards. The disposal signal goes through. And this is, of course, process supervision. It comes for free from the DAG. So this is how electric DOM works. Every single DOM element on the page, you have thousands of them, is each an individual concurrent process. It has inputs, it has outputs, it has point mutations, it has effects. And it is just completely choreographed by the DAG. And when you want to dispose of a resource because of a control flow outcome, it will just propagate through the DAG backwards. And this is also how electric supervises your network connections. So let's suppose right here, instead of a static literal, we had a clock. Hope I didn't make a typo, I might have. Okay, there it is. So what's happening now is instead of allocating the DOM or the literal, we are connecting to the server and we are allocating the clock signal, okay? And then when it switches false, and you also need to subscribe to the change feed. Then when it switches false, you need to dispose of the signal on the server, unsubscribe from the network change feed, and then unmount the DOM text and the DOM H1. So all of this comes for free out of the DAG. It's just supervision. So network connections, automatically managed. That's pretty cool. The two major results, in my opinion, of functional programming are functional reactive programming and functional effect systems. What we are doing here is we're showing a unification of them. We get both reactivity and we get the object lifecycle at fine granularity. So what electric is, it is direct style syntax for functional effects. And by the way, you'll note this clock constructor is impure. There's no arguments. In Haskell, if we tag things with IO, we get to call them pure. And electric is direct style syntax over functional effects. So can we call this pure also? Okay, next we're going to talk about query cancellation. In fact, let me go back to our problem statement slide. So we've done this, resource disposal, query cancellation. So for this one, we're going to go back to we're going to go to a new demo. This is the t-shirt orders demo. So what this is doing is there's a database query for t-shirt orders, and you get an email address, you get a gender, and you get a shirt size. Okay, and then these two things are pick lists, and the pick lists are filtered on the server because it's an enterprise app. What if the collections are really large? I can make that a little bigger. All right, let's take a look at the code. So here is the filter, Alice, and here it is. So this is on the client. The database is on the server. The string Alice is on the client. And server client, that's the query. And here's the return of the query. You get a collection of IDs. You loop over the collection, you draw the table, you switch to the server, and so on. You continue rendering. Let's go into the query. So here, server client, server client. Here is the actual database query. It's coded in Clojure. It runs on the JVM. So this is we're using the Atomic database, but it's like, this is on the JVM. It's not on the client. So this here is the first time where the search, the string Alice from the input, was needed on the server. And the front end knows this from the DAG, so it anticipates this and it sends it up without being asked. Okay, we run the query. What offload does is it moves this query to a thread pool because it could be slow in blocking. Okay, so electric is a fully reactive computation. It's asynchronous even on the back end, so we don't want you blocking the asynchronous computation with a slow query. Oops. So what happens if the query is slow? When you type here, one character at a time, each of these individual changes is showing up right here, and electric will rerun the function with the latest value from the client. And if the function is slow, what offload will do is it will interrupt the query, interrupt the thread, and dispose of those resources. And this happens transparently and automatically by electric, and it happens because of the DAG. So this is just process supervision. A mistake many front-end frameworks will make is they will debounce their inputs. So they may add a 300 millisecond debounce right here to avoid smashing the server with a burst of queries as the user types. This is a really bad mistake because you're adding 300 milliseconds of artificial latency to every single interaction. Okay, what you want to do is you want to send the information to the server as fast as possible, even saturating the wire, the resources available, and let the server run the query as fast as possible and dispose of the stuff that no longer matters. And you want this to be automatically managed. Okay, so adding this artificial latency is just a horrific mistake. Okay, quickly, let's demonstrate Lambda. I'm going to make this a little bigger. So here is a Lambda. Okay, so recall in this example, we have the women's pick list, and you have a function that contains the pick list options, and you only call it when the pick list is open. You only want to load those when you ask for it, okay? So what is a Lambda? It is a higher order DAG. DAG is a value. Okay, now it's a compiler, so the client and server, they share the source code, so all you need is a pointer into the AST for them to get the static information about this value of the DAG, okay? So Lambdas are transparent, and this transparency is what makes the choreography work. It means they can look inside this function and figure out the network connections and plan it out based on the static knowledge. So what happens when you open the pick list? Well, this function will boot. We have this DOM input, the filter, and let's take a look inside the type ahead very quickly. You have this isOpen signal, true or false, and if you're open, you call the options query with the value of the search on the client, okay? Oops. Oh no. Go back. So here it is, search is on the client, it plumbs here, gender is on the server, database is on the server, and it just works. So splicing or calling a Lambda is just splicing the DAG at runtime. I also want to call attention that this pick list, it only shows the women's shirt sizes because Alice is female. So what happens if someone changes the gender of the t-shirt order? Say someone else does it in a multiplayer situation. So what the database will change, and the value of the entity will change, and then the gender query will rerun, and the gender is used in 2 places in the DAG, and it will just reactively update by propagating the DAG, and the pick list will update with the new option values. Okay. So if we have Lambda, let's push that a little harder and see how far that can go. I'm going to use 2to-MVC as the example for this. Oops. So here's 2to-MVC. It's interactive, it's multiplayer, and this is because it's not a client-side database. Electric gives you the server by just like syntactically saying server. So it's basically free. It costs 0 lines of code to make it use a backend database. So anyway, 2to-MVC is not the point. The point is we are modeling this 2to-MVC as a function. The network connections, the DOM effects, the server, all of it is just a function. So let's look at that function. Here's your 2to-MVC function, and we're using partial function application here. Oh no, I've made a mistake. What I want to know if something's really a function, you need a test for that. So the test I like is to compose it in a list. You should be able to call a function in a list if it's really a function. So let me increase the cardinality of this loop. and save. So there you go. So now you have to-do-MVC called 3 times, and it still works, right? It's still multiplayer. And they're synchronized, and that's because they are bound to the same scope. So here's the to-do-MVC function. We're using partial function application. The database is on the server. The state is on the client. The form edits as I interact are on the client. And those are just being resolved from scope. So this is a thunk, app as a thunk. We pass it into this popover cascaded function, which what that does is, all it's doing is like managing the staggered DOM layout for this CSS. And then here's our function, and we splice the function right here, we call it, and that's really all there is to it. Calling a function is splicing the DAG. There's also dependency injection. Binding is Clojure's operator for dynamic scope, which lets you put something like in the environment, basically. In React, classic React terms, that would be React context. And we have it. It is, of course, reactive. It has the object lifecycle. It is supervised. It has client-server transfer. Okay, so that's really all there is to it. Okay, we're halfway through the talk, and we have not even talked about differential data flow yet. So let's motivate that. Back to the T-short orders demo. So recall we use E4 to loop over the collection. That came from the database query, okay? So let's look inside the database query. So here we go, database on the server, search on the client, we pass it to the real database, we get the result, and here's diff by. So if you know React, you already know there has to be diffing somewhere because React taught us we need to stabilize the DOM. You can't just blow away the DOM. So what we do is, instead of diffing at the last possible second, the virtual DOM like React, we diff as far up the DAG as possible, and we do this so that we can get diffs on the wire. You want differential network traffic, okay? So what diff by will do is, you need to provide a logical identity. It will call that function on each element of the collection result so that as I filter this, you can get a change set that says, okay, Bob is gone and Charlie is gone. And you get a change set right here that says that. We've lost Bob and Charlie as a subtraction. Okay, what that means is that IDs is not a collection. IDs is a stream of diffs. E4 is reducing over the stream of diffs, right, inspecting them as they go through, and then materializing the items in the DOM. Okay, at no point in your program, except for in the DOM, does the collection exist to userland. So let's take a look at the diffs. We have a function tap diffs. Tap diffs IDs. Oops, okay. Need to make that bigger. So we start with 3 items in the collection, and now I filter it down, and what you get is a diff that says shrink 2. So it's popping from the end, so you started with 3 items, we took off the back 2, shrink 2 is all you needed. When you bring it back and clear this filter, you got a grow 2, and here's the change set, the new values for the items you're adding. Permutation is how you reflect order over the network. So what if like Alice and Bob change places in the order based on the database sort? You need to reflect that in over networks so you can like rotate them in the DOM. That's permutations. So what's the point? The point is you're really getting diffs through the DAG and diffs on the wire. We're not sending collections back and forth. If you send collections back and forth, you're going to hit ceilings, right? There's only so much you can brute force that. You're going to have ceilings in terms of the size of the collection, ceilings in terms of the number of collections you can have, ceilings in terms of how fast they can update, and ceilings in terms of like the dynamism like downstream of that and the reactivity downstream of that. And the bigger your app, the worse it gets. Okay, so Differential lets you do this in constant time. So as an example, this is an app built in Electric. It is a shipyard crane, a digital twin of a shipyard crane robot that is loading fish meal onto a boat. And we are streaming events from the robot at 20 hertz to this observability UI. And we're actually logging the events so we can get playback controls like pause, fast forward, rewind, okay? So what we're about to do is rewind at 40x speed, so we're going backwards at 40x speed, and now you can see like we're streaming stuff in at the edge, right? React just can't do this. You couldn't possibly re-render the collection over and over. You have to have incremental loading at the edges. Now, this is a great point to talk about back pressure, okay? The robot's playing at 40x speed. It's way too fast for the client to replay all of those events one at a time, but you can't drop events because you'll corrupt state. Okay, so what do? Well, differential data flow to the rescue. Diffs can squash. If the network is slow, the server will reduce the diffs with an accumulator function, which is the diff squash operation, okay, the diff squash semigroup. And then when the client is ready, it will just get a larger change set, right? So when you slow down, you're just going to get chunkier diffs. The sleight of hand I've done here is I've switched from events to diffs. So what are we diffing? What we're diffing is this collection in the DOM, okay? This is a window over the event log. It's no longer the events, it's a window, and that's a value. The collection is a value. Values can be diffed. You use our diff by operator, and now you get change sets for this window, regardless of if your last time you sampled it was 10 milliseconds ago or 10 seconds ago. You'll just get a very large change set. So that's the trick. So how does something like this map to virtual scroll? Right? We want to use this efficient diffs on the wire to get virtual scroll. So first of all, you need the offset and limit from the DOM as the user scrolls, right? The scroll offset. And then you need a strategy. Maybe you want to just stream the offset to the server and give it to the database, okay? Which maybe it can fulfill that fast enough. What we're doing here is we're actually looping over a file system. So we reduced the file system, sequenced that into an array. We're just windowing over the array based on the offset limit. And you can do that in like 100 microseconds. Okay. So as I swipe down, me on mobile or a laptop, right, you can see the loading is at the edges, and you do get diffs on the wire, okay? But what if instead of swiping gently, we abruptly scroll, okay? This is a random access seek, okay? So there's not a lot you can do in terms of like reusing the prior state and having a nice, good change set diff. However, it's bounded in size by your viewport, okay? So the differential structure handles both of these. The less abruptly you scroll, the more laminar and smooth your diffs will be. And if you start scrolling more abruptly, the system will do its best, and you'll get chunkier change sets. An example of where it really shines if I start smashing the scroll, and now we need to talk about query cancellation again, right? So what will happen is as fast as possible, we're streaming the offset limit to the server. The server will do its best to fulfill. Even this, when you're doing a 100 microsecond window over a sequence in memory, you still can't keep up because you're smashing these DOM events fire way faster than that even. The DUF, it's just very fast. And differential data flow will just seamlessly like scale your change set sizes, and it will do its best to saturate the resources available to you so the system stays responsive. And this is all managed by the framework. You don't have to do any of this in userland. Okay, there are two examples left. Now that we have back pressure, we can talk about a chat app. Now, let's pretend the web view is a chat app because I don't want to boot up a new example. We're just going to pseudocode on this one. So if you want to make a chat app, you need to do two different things. First, you need the initial state of the query, okay, the channel history. But also, when someone sends a message, you need to like subscribe to a Kafka topic or something, and you have a callback, and you need to merge that in and reconcile it with the first query. Now, we can't solve that for you. That's your data layer. That's your problem. But what you do is you reconcile those two sources inside this function, and then you get diffs. Okay? The diff doesn't matter where it came from. The E4, in fact, like it just gets diffs one at a time. You know, it doesn't matter whether it came from the Kafka topic or the database query, and there is no change to your userland program whatsoever. Okay, the differential data flow handles both of these cases seamlessly. Okay, one final magic trick. This is optimistic updates. Let's say when you send a chat message in Slack, you want to see your own message updated without waiting for a round trip to the server. So what you would do is, well, we have this function, which is returning the new events as a value, okay? And what you can do is you can loop those edits on the client back into the function. So this is pseudocode, by the way, but what this is a recursive data flow binding. And then you have the edits here. So now the query, not only does it have your database and your Kafka topic streams, and it also now has the local updates. And the E4 just doesn't care. It doesn't care where the diffs came from, if it came from locally or if it came from the WebSocket. It just doesn't matter. And you can represent your full stack application as this data flow circuit. So for the record, we're not certain a Haskeller would recognize this as the arrow loop type class, and we know from the literature that signals indeed have a arrow loop instance. It's unclear if differential signals do as well. Nonetheless, this pattern it shows a possible path forward of how to model a full stack application as a pure function using recursion. So there you have it. The computational structure of user interfaces matches differential data flow. You get the process supervision, you get the back pressure, and you get the incremental collections, and you get all of this under the easy, simple, functional-like composition model of Clojure that anybody can understand. I'm Dustin Getz. This is Electric Clojure. Check it out.